Okay, well, here we are. Stats 102C, the Monte Carlo methods, right? Okay. Thoughts are a little bit scattered right now. Okay. I was going to go over a little bit of the syllabus, but I can't even pull that up. It's available on CCLE. You can read through it. Pretty much, we're in summer session, so we've got 6 weeks, and then and each week we meet twice, right? And then for 2 of those, for one, we're taking exams. So on 3rd week, Thursday, we've got a midterm, and on 6th week, Thursday, we'll take our final, okay? Which leaves us with 10 sessions, and each session's about 2 hours, a little bit less, and I wasted like 17 minutes. So we've got to compress a lot of stuff into our sessions. And then, and on top of that, well, not on top of that. Yeah, there's just a lot to cover. I'm going to have to cut some stuff from the normal 10-week course. And I hope you guys aren't going to be too heartbroken about the stuff we miss. But I'll still try to do this topic of Monte Carlo methods justice. Okay, so what do you guys know about Monte Carlo methods? Or what about, what is the Monte Carlo? Maybe we'll start there. Nobody for what the Monte Carlo is?
Is it a casino?
It's a casino. The Monte Carlo is a casino in Monaco. It's like, I don't know, one of those little city-state nations, okay? So the Monte Carlo is this is a casino. And it's kind of like, when you hear the word Las Vegas, you think of gambling and casinos, or at least in the United States, when you hear Las Vegas, you think gambling and casinos. And when Europeans think of gambling and casinos, they think Monte Carlo. That's the place that comes to mind. And the idea there and the reason why we call this Monte Carlo methods is because in the casinos, you're playing these games of chance, which has this random aspect to it. And those games of chance are played many, many, many times. And the casino makes its profit because the games are designed in such a way that over the long run, the casinos make a profit, okay? But, of course, on any given day, a player could get lucky, and the casino might give that player more money than what the player brings in. But overall, across thousands or millions of people and millions of games, the casino keeps their edge, right? Okay, so the Monte Carlo is a casino, and when we talk about Monte Carlo methods, we're talking about this is basically using randomness to answer tough math questions. Okay, using randomness and really many trials to answer tough math questions. Okay. So in I think one of the prereqs for this class is 100B, and 100B is your mathematical statistics course, right? So stats 100B. So let's contrast this class to do 100A and 100B, right? So you got mathematical statistics, and in that, you looked at different random variables, different distributions, right? So you studied random variables and distributions. And what are some aspects of a random variable or a distribution that we might be interested as statisticians or whatever? So we would want to know things like the mean. Okay.
Frequency of outcomes.
What's that?
Frequency of outcomes.
Okay. The distribution itself. But certain aspects we might be interested in the mean. What do we call the mean? The expected value, right? Okay. So you studied random variables and distributions, and then you might be interested in the expected value. What else might we want to know? You got the expected value. What's the other thing that usually goes with that? The variance, right? Expected value and variance. Okay. And then there's other aspects, but these are probably the two primary things that we learn about or try to calculate and figure out. Okay, and how does one go about calculating the expected value of a random variable? So let's say we have random variable x. How do we calculate the expected value? You guys learned this, right? Okay, so how do we get the expected value? Let's assume it's continuous. Okay, so we got random variable x, a continuous random variable. How do we get the expected value? What's that?
Integration.
Integration, okay, and what's the integral that we do? So you do it over the domain of x, right? Whatever it is, negative infinity to infinity, 0 to infinity, 0 to 10, whatever it might be. And then what do we have? T times probability of t dt, right? Where probability of p, this is the distribution, right? This is the density of x. Okay, and this is what we did in 100B. Okay. And then with the variance, what did we do? You had to do this minus the expected value of the variance of x would have been right, something like that, I think. And which then simplifies to the expected value of, wait, is it x squared minus? It's this, or is it the other way? Yeah, it's this. Okay. Okay, so this is what we did in 100B, right? And sometimes this got hard, right? Sometimes integration is a hard thing to do. And I'm actually really bad at integration. And so So I struggled doing all of the integrals and all of the complicated math, right? This was like, I get these concepts, but then when it comes time to actually doing the integrals, it's like, oh man, I don't know how to do this integral, right? There's all sorts of little tricks. I end up just going to Wolfram Alpha and saying, give me the integral of this, please, because it's hard. So this is the big picture of Monte Carlo methods. Big picture Monte Carlo methods is we want the same stuff that we want from 100B, okay? We want to get aspects, we want to learn about aspects of a random variable. We want to know the expected value. We want to know the variance. We want to know these properties about random variables or distributions or things like that. But we want to avoid doing this math because this math can be hard, okay? And so Monte Carlo methods is, can we use a computer and its random ability to generate random numbers, can we use that to give us approximate answers to these things, okay? So Wolfram Alpha is great at integrating, but it actually had to learn, or they had to like program a bunch of these little tricks and stuff so it can actually, kind of do some integrals, okay? We're not trying to do that. What we're trying to do is we're just trying to say, can we get an approximate value for this expected value and an approximate value for the variance, okay, without having to do these integrals? Okay, that's kind of the big picture of Monte Carlo methods, okay? So what's the whole point of this class? Okay. Big picture idea, okay? We want to learn the same stuff, okay? Expected value, variance, expected value, variance, what else? Other properties, okay? But we want to avoid the hard math. Okay. So we want to avoid doing, those integrals. Okay. Or, there's other things that we can do. Not necessarily just avoiding integrals, but it's the idea. We want to avoid the hard math, and the idea is all we're going to do is we just kind of run simulations or just do repeat something many times. And we get an approximate answer, okay? So our solution, our Monte Carlo solution, okay, draw random values from the target distribution. So this is the distribution you wish to learn about. So our solution is just going to draw random values from the target distribution, and I should say many. And then and those will stand in for kind of the distribution itself. Those values stand in for what the distribution itself is, and then you take the mean of those values you draw, or the variance of those values you draw, okay? So draw many values from the target distribution and use those values as a kind of a stand-in for the distribution itself. And then get approximate values. Of the expected value or variance or whatever else it might be. Okay. And because we're not even worrying about the complicated math, this allows us to kind of tackle very complex distributions, eventually to a point where we won't even know what the density of X looks like, okay? We won't even know, we'll just have we will know that it is proportional to something. We know kind of the shape of the density, but we don't know the actual formula for the density, okay? So, because at this point, it's like, the math might not even matter, okay? And so this, allows us also to handle distributions where the exact density is unknown. Okay, just only known to a proportionality constant. So I mean, we'll know the shape of the distribution, but we won't know the actual equation. We'll just know it up to a proportionality constant. Okay, does that kind of make sense as far as where we are headed? Okay, so this is kind of the overview in a nutshell. In our class, we'll also cover a little bit of Bayesian statistics, because that's really where Monte Carlo methods and its uses are, in my opinion, are most powerful and most useful, okay? Because you end up in this situation here, where the exact density is unknown, you know that you end up in this situation quite frequently in Bayesian statistics, okay? In Bayesian statistics, you'll end up distributions where the exact form is unknown, but it's known up to a proportionality constant, okay? And so we end up here a lot, and so Monte Carlo methods allow us to answer the questions, even though we don't know the exact form of the density. It's worth putting up Bayes' rule just to kind of remind you of that. That's dangerous. Yeah. It's like, that's bad design. Pinched my finger. Alright, okay. Don't use the handle because the handle will, Alright, it's okay. All right. Okay. Yeah. So we have applications. Bayesian statistics. No. Has anyone taken a course in Bayesian statistics? Yeah, I didn't think so. Right. So I'll have to introduce some basic Bayesian statistics concepts here. Okay. But we got applications in Bayesian statistics. This will come later. I'm just giving you like a peek of whatever we're going to be doing in this class. Right. Okay. So do you guys remember Bayes' rule? All right, so Bayes' rule says, let's say you want to know the probability of B given A, and this would be the probability of, it's going to be A and B divided by the probability of A. And A and B can be simplified to probability of A given B times the probability of B, and then on the bottom we have probability of A, right? Okay. In Bayesian statistics, this often becomes, we want to create you'll have the probability of some parameters, maybe parameters theta, given the data D, okay? And using Bayes' rule, this can be simplified to the probability of the data given the parameters times the probability of the parameters divided by the probability of the data. Okay, all I did was just plug this in. This is complicated and hard to find, the denominator. Probability of the data. So all we do is we say, well, you know what? I don't even want to calculate that denominator. Okay? I could say the probability of our parameters theta given the data is proportional to the probability of the data given the parameters times the probability of the parameters. Is that okay? And then we just use this. So we don't have the exact density, but it's proportional to this. Okay, this is a constant. It's a constant, but it's complicated. It's a complicated and hard to find constant. Okay. Why do we need to even have this constant in here? I mean, it's mandated by Bayes' rule, but what's the purpose of what happens? What's the what are properties that are true for all probability distributions? There's two of them. Yeah. Integration over the whole domain is 1, exactly. And then the other one is that it's always positive. Okay, it's never negative. And that's all this serves, okay? It's just, this constant is here so that when you integrate over the entire domain, it integrates to 1, okay? If you take any function or whatever, and if you just throw in a different constant, then the thing might not integrate to 1 anymore. And then it no longer qualifies as a probability thing. Okay. But that constant can be complicated to find. All we do is we say we're going to deal with this. Okay. And Monte Carlo methods allow us to work with this rather than this. Okay. Allows us to just work with something that's proportional to the thing. Even though it doesn't integrate to 1, Monte Carlo method says, oh, you know the shape, that's good enough. Don't worry about this integration stuff, or integrating to one stuff just yet, okay? Okay, so that's Monte Carlo methods, the big picture idea. And so this first week, we'll just talk about this part back here. Drawing many random variables from the target distribution. That's what we will look at first. Okay, we'll start there. And then we'll build up from there, okay? So this is this week. We're going to draw a bunch of random values from the target distribution. And then we use those values as a stand-in for the distribution itself. Yeah. That's so it's kind of like this, right? If you have a fair die, okay, so if you have a fair die, then when you roll it, each face should show up with probability what? 1/6, right? Fair die, each face should show with probability equal 1/6. Okay? Now, I don't know, imagine this was the Wild West and you, I don't even know, I'm just making stuff up here. But let's say you took the die and then you, I don't know, sanded off one of the corners or something, you doctored it somehow. And you're hoping this will now give you an advantage to the game of chance that you're gonna play, okay? But what happens to the probability of the die when you shave off one of the corners? Like, is that going to increase one of the sides? Which side does it increase? Which side does it decrease? I mean, obviously, if it increases one of the sides, then it's got to decrease somewhere else because everything has to add up to 1, right? So if you doctor the dice, if you mess with them, how does that affect? Now, maybe we could go over to the physics department and say, all right, tell me what, the properties of, I don't know, a rotating cube. Well, not quite a cube because we've messed with, some of the edges and stuff. And we could ask what's going to happen. And maybe they could do the math and tell us, when you do this to one of the faces or one of the sides, it's going to increase the probability of this side. I don't know, okay? It sounds really complicated to me, and I would not want to have to do the math involved in figuring that out. So what's our Monte Carlo solution? Okay, so let me just write this. Okay, so we got the fair die. Okay, let's doctor die. Okay, so maybe we'll shave off a corner. Okay, how does this affect the outcomes? And the answer is, maybe we can answer this mathematically using rules from physics, right? but that sounds like it's going to be hard math. Because I don't understand physics. I don't know physics well enough to be able to answer this question. Okay, so the Monte Carlo solution it says, I don't want to do hard math. I'd rather do a bunch of menial tasks many times to get my answer. So the Monte Carlo solution would say, just give me the die, I'm going to roll it 1,000 times, and I'll tell you your answer. Okay? That's the Monte Carlo solution. So it's the opposite of working smarter. It's just, what is it? Don't, work smarter, not harder? No. Monte Carlo solution says, let's just do the menial task millions of times, as many times as we can, and get the results. Okay, Monte Carlo solution, let's roll the die lots of times. Let's see what happens. Okay, how many times do we think we have to roll the die? And the answer is, I don't know, okay? And this is the hard part, is in the Monte Carlo solution, if the difference that it makes is really pronounced, you only have to do it a few times, right? You only have to do it maybe a few hundred times. If it's like, after doctoring the thing, it should, side 6 shows up, way more often. But if the change is subtle, then you probably have to do a lot more simulations, okay? Or a lot more of these things. And if it's a physical die, this is probably going to take a very long time, and it'll be very tedious and whatever. And you'd want to have multiple dice that were doctored in the exact same way, and then maybe you can come to an answer. Who knows? Okay. That's the Monte Carlo solution. Obviously, in this class, we're not going to take physical dice and roll them, but we will try to, do something similar in terms of drawing values from a random variable. Okay. But yeah, I guess maybe we can't do the hard math. We'd have to build some kind of computer simulation, which now suddenly makes it way harder. Okay, is that all right? This idea of what the Monte Carlo solution is to things? Okay. All right, so we're going to start off with okay, so we want to generate values from a random variable. Okay. And we are going to start with the assumption generate values from a random variable. Okay. The assumption. We can draw values from random uniform. So we're going to say we are able to draw values from the uniform distribution from 0 to 1. Okay, that's going to be our assumption. We're going to say our computers are able to do this. Okay. This used to be a very, like in a Monte Carlo class, you would spend a few lectures on this topic of drawing values from uniform 0, 1. Although today, this is kind of like a solved problem now, okay? We've got high quality pseudo random number generators in the computer, okay? So we have, okay. So this assumption is okay now, all right? But it used to be tough, okay? And in fact, before we have laptops and before, you could just go onto R and say RUnif and whatnot, people would buy these tomes of random numbers. It'd be like a dictionary, except every page was just random digits. It'd be like 1 billion random numbers, and it'd be like 1,000 pages in each page. Well, I don't know, maybe more. I don't know how many pages, but you would just buy books of random numbers that somebody had generated for you, and you would use that for your random numbers. But now we can just go on the computer, say RUnif, right? RUnif1 just says give me one random number, and it's going to give you a number between 0 and 1, right? Our computer, the default pseudo-random number generator is the Mersenne twister. It's a complicated algorithm to generate random numbers, but it's very good. It's passed a barrage of tests. Maybe I'm dwelling too long on this, but I guess at the core of it, there's a question of, is a computer able to give you true random numbers? And it can't, because the whole point of a computer is that it behaves in a predictable way every single time you give it the same instructions. But you're asking for it to give you a random number, so what can it do? It uses a pseudo-random number generator, which produces values that sure look like random numbers. But that's why you can set a random number seed, so that anytime you run the program again in the future, you get the exact same random numbers that you did last time, okay? Is that all right? Any questions? Okay, so anyway, we're going to assume that we can draw values from the random uniform distribution, okay? And we will start with the most basic form to get random values, and that is called the inverse Cdf method, okay? So if we can get values from uniform 0, 1, okay, we can use the inverse Cdf method to get values from any the CDF? CDF stands for cumulative distribution function, right? Okay, let's, you guys remember this stuff, right? Okay. I'm getting blank stares, so. Oh, okay, so we're gonna use the inverse cumulative distribution function. See this one won't pinch my fingers. This one does. I don't know what's up with that. Okay. Okay, so let's say we've got the normal distribution. Okay, what's I forget what the normal distribution is like. Okay, so the normal distribution, the PDF, which stands for what? Probability density function, which is for continuous distributions, right? Okay, so for the normal distribution, the PDF looks like what? This looks like the normal distribution that we're all accustomed to seeing. Okay, looks like that. Okay. What does the PDF goes from negative infinity to positive infinity, and the integral from minus infinity to infinity the normal density, this would be equal to 1, right? Okay. What is the cumulative density function? Here, wait. What's the exact form? I should write this down. Okay. So the normal density. Let's go to Wikipedia. It's 1 over square root normal distribution. It's like 1 over root 2 pi, right? Okay, yeah. 1 over the square root of 2 pi e to the negative x squared over 2. Right? 1 over root 2 pi e to the negative x squared over 2. Okay, so that's your PDF, the normal distribution. And what's the CDF? The CDF is equal to the integral from negative infinity to x of 5t dt, right? So we just take our PDF, we do t's, and now we get the integral from negative infinity to x. And what does this thing look like? It looks like this, right? It goes, and then right here, it goes there, and then something like that. And it goes from 0 to, as it goes to infinity, it goes to 1. Okay. So this is our CDF. Let me And so the CDF maps x to the interval uh, 0, 1, okay? And so, should say this is capital F of x, or big phi of x, okay? So this is the probability integral transformation. This is our theorem. You know how. I'm not really going to try to prove any of this stuff here. Okay. But I'll write it out. Okay, so this is the probability integral transformation theorem. And this says if x is a random variable with cumulative distribution function f of x, then f of x itself comes from the uniform distribution from 0 to 1. Which basically says if you draw a random value of x from here and you plug it into the CDF, then f of x will produce values between 0 and 1, all with equal probability. Okay. Little x from the distribution f of x, and f of that will be a value drawn. We can do 1150, right? Okay, so we've got this. All right, let's then do our inverse CDF, okay? All right, so we want the inverse CDF. Okay, so the inverse CDF is the inverse function of f. So the CDF is f of x, and the inverse CDF is going to be f inverse of u. And this is equal the minimum value of t such that f of t is greater than or equal to u for 0 less than u less than 1. Okay, now that looks funny. The inverse. Okay, and the whole point of this thing is so that it can handle CDFs that for either continuous or discrete distributions. I'll show you an example of a discrete one in a moment here. Okay, the min stuff. Is there so it works. For discrete distributions. Okay, so the inverse CDF transformation. Okay, so we're going to say U comes from uniform 0, 1, and then if we take the inverse CDF of U, then this will come from the distribution of F, okay? Or, so yeah, so values of U come from uniform 0, 1, and then if you plug that value into F inverse, it will generate a random value from the distribution of X, which is exactly what we want. Okay, so if F of X for the normal distribution looks something like this, right? Okay. Then the inverse, right? When you take a function and you do its inverse, you get you flip it along the axis y equals x, right? And so this becomes something that looks like that. This is the x-axis. Okay, is that all right? Okay. in R, what do we use to get the CDF of the normal distribution? What are the functions you use to access the normal distribution? Okay. There's D norm, and P norm, and Q norm, and R norm. You guys know this? Do you guys have your laptops that? Okay, if you have your laptop, you can try messing with R, but you guys have used those functions, right? Or no? Okay, so D norm will plug in, will give you the density, okay? So the D norm is this function. Okay, so this function here, oh dear. This one is D norm. So if you plug in D norm 0, what do you get? D norm 0 is equal to the 1 divided by the square root of 2 pi. Because you plug in 0 here. And 1 over root 2 pi. I don't know what that is. Can someone verify that? Did that work? What's D norm 0? No? Okay. Thanks for that. Okay, well anyway, D norm 0 will give you this. Or is it not lining up? I see people with laptops. Nobody's got R open on their machine. What's that?
0.39.
0.39. So D norm 0 is 0.39, and then if you did 1 divided by square root 2 pi, do you also get 0.39?
Yes.
Yes. Okay. Good. So that means I'm not lying to you here. Okay. So D norm is this function right here. Okay. And then you can also the PDF. You know, there's also a sigma and a mu term if you wanted to mess with that there. But basically, you plug in D norm, any value, and it's this function right here. Okay. What will, before you type it into your computer, what will P norm of 0 give you? So that's this function. The function for the CDF in R is P norm. So what will P norm of 0 equal? P norm of 0 is equal to 0.5. P norm is the same as your cumulative dense distribution table. And you know, at the back of your stats 10 book, you have the normal table. That's what P norm is, okay? So what is P norm of 1.96? P norm of 1.96 should be 0.975, right? Because if you go to 1.96 and negative 1.96, you get the middle 95%, right? So P norm of negative 1.96 is 0.025. And that's how we say plus or minus 1.96 gives you the middle 95%. Okay, so that's P norm. Okay. The inverse here is Q norm. Okay? So what would Q norm, I don't know if this will even work, but what would Q norm of 0 give you? Q norm 0 should give you negative infinity. Okay? Because that's what we've got. Right? It's what value do I have to plug into P norm for it to produce 0? Well, I have to plug in P norm of negative infinity will give me 0. So Q norm of 0 says the value you plug into P norm is negative infinity. Okay? Q norm of 0.5 would be what? This is 0. What is the value I plug into P norm to give me 0.5? That's Q norm. It's the inverse function, right? So Q norm 0.025 is negative 1.96. Okay. Is that all right? Who's got their R laptop open to R right now? Somebody got it? You got it open? Or somebody? Okay. So okay. So disclaimer, the inverse so I never actually showed any math, right? I just wrote the PDF here, and then I said the CDF is this, okay? Disclaimer is that there isn't a closed form solution to this, okay? The CDF of this thing is like really, really hard, okay? Trying to integrate this, it's really hard. There isn't a closed form solution. But we've got some really, really good approximations that are fast, and that's actually what your computer uses, okay? Your computer doesn't, when you ask for the P norm, it's doing an approximation. It's like accurate up to 16 decimal places, which is good enough for our purposes because our computer, because of floating point arithmetic, only is accurate to 16 decimal places anyway. So for all intents and purposes, on the computer with a floating point, 64-bit floating point precision, it's good enough. Okay, but if to do the actual math here, this is really, really, really hard. But anyway, the computer, when it does P norm, we're going to pretend that it's good, okay? And when it does Q norm, it's doing the same thing, and it does this. And the computer actually uses the inverse Cdf transformation when you ask for random normal numbers, right? So on the computer, how do we generate values from the normal distribution at random? We don't use D norm or P norm or Q norm, we use R norm, right? You guys have used R norm to get random normal numbers, okay? Maybe you sat and wondered, how does this work? Maybe that thought has never crossed your mind, okay? R norm uses inverse CDF method. It takes numbers from R unif, the random uniform, and it takes those random numbers and plugs them into Q norm, the inverse CDF function, and it produces values that it then uses for to say these are random normal numbers. Okay, and if my computer worked, I would show you. I'm trying to get. Is there like a? There is a web server for R. Let me see if I can find the online RStudio. Let me just see. Let me see if this works. Maybe. Oh, shoot. Okay, we're gonna try this. These were RStudio. Maybe I can get this to work. Maybe not. Okay, let's see. All right, let's. Maybe I can get this. Okay. So, tools, local options. Just bigger. Text a little bit bigger. Okay, so you guys see that in this thing? Okay. Okay. All right. So I'm going to do. So here's our unit. And we can ask for 10 random numbers from 0 to 1, and this is what it says, okay? And then, because it's a computer, you can do set C, and we'll just do set C1, and you ask for 10 random numbers, and it gives you 10 numbers here. If I go back and I say set the seed again back to 1, and ask for 10 numbers, it's going to give me the exact same values here, right? So that's random uniform. This is okay, right? All right, let's take a look. Let's do set seed 1, and we'll say ask for 10. We'll just do 5 random normal numbers. Okay, so when we ask for 5 numbers from the normal random distribution, these are the values it gives me. Okay, and what I want to show you is that what R is doing is it's just taking the same numbers from random uniform and it's just plugging these into the inverse CDF function to get this, okay? But it does every other number. So it does this one, and this one, and this one, and this one, and this one, okay? And it produces these numbers. So let me just show you. If I copy this number, so I'm going to copy this number, and I'm going to ask, what is the inverse CDF of 0.2655? It gives me the first random normal number. Okay? And if I say, what is the inverse CDF of this? Okay, it's giving me this. Right? So when you're asking R to produce asking R to produce random numbers from the normal distribution, it's taking the random uniform numbers and it's plugging them into its inverse CDF function, QNorm, to generate these values. For whatever reason, it only does every other number from random uniform. But that's what it's doing, okay? So we generate random values from our target distribution by using the inverse CDF. So the CDF is the cumulative distribution function that maps from the domain of x to 0 to 1, and then the inverse just inverts that and says, now I can take values from 0 to 1, random values from 0 to 1, and it will map to the domain of x. Okay? And so that's an example using the normal distribution, but this can then be extended to excuse me, any other distribution that we want to do. Okay. Are there any questions on this? So now you know a little bit of how the inner workings of R's random normal thing goes. Okay. But you should at some point read up on the normal distribution, and this gives you the details. Distribution, the quantile. Oh yeah, they call it the quantile function. The quantile function is the same thing as the inverse CDF. And yeah, so P-norm is based on this, a portable Fortran package of special functions in this, published in 93. In Q-norm, the code is a C translation of this, percentage points, which provides precise results up to about 16 digits, okay? So which is good enough for us, okay? But that's because for the normal distribution, a closed form thing doesn't exist. Okay, that's all. All right, so I posted up your first homework, which involves generating some random values, some basic stuff here. All right, okay, so let's do so we did the normal example, and then this is just kind of general rules. Okay. So to generate random values, from a distribution. Okay, so first you have to derive the inverse CDF. And so this might involve some calculus, okay? So you may have to do calculus. Okay, and then generate U from the uniform 0 to 1. And then let x be equal to that. Okay. All right, so let's do a different example. And this will be the exponential distribution. Okay, so the PDF of the exponential distribution is lambda e to the negative lambda x, okay, for all x that are positive, greater than or equal to 0. And the CDF is going to be the integral from 0 to x of lambda e to the negative lambda t dt. Okay. All right, and so when we do this, we end up getting 1 minus e to the negative lambda x. Okay. So the CDF is that. And okay, and so if we want excuse me, then to invert the CDF, okay, we are going to set this inverse CDF. What we do is we set f of x equal to u, and then and solve for x. So I'm going to do 1 minus e to the negative lambda x is equal to u, and then just doing some stuff, I get 1 minus u is equal to e to the negative lambda x. I get natural log of 1 minus u is equal to negative lambda x. And so I get x is equal to negative 1 over lambda log of 1 minus u. So this here, this is my inverse function of u. Okay, so I've got the inverse CDF is equal to negative 1 over lambda log 1 minus u. Okay, and then now all we do is we say, okay, generate u from uniform 0 to 1, plug in those values here, and that will produce random exponential values. Okay, plug into f inverse of u, okay, and you get random exponential values. Okay, and then in fact, if u comes from uniform 0 to 1, then the value 1 minus u will also come from uniform 0 to 1, right? You're just kind of flipping your perspective. And so a lot of times when you ask what is the inverse, not the inverse CDF, but what's the algorithm that we use? So it simplifies. All right, is that okay? Okay, and then, well, I don't know. Okay, any questions on any of this? Yes?
Can you explain the 1 minus?
Yeah, okay, so the idea here is if you have a, like, so let's say U is a random variable that comes from the uniform distribution 0, 1, okay? And let's say we have another variable called V, and V is just equal to 1 minus U. Okay, so if U comes from uniform 0 to 1, and V is equal to 1 minus U, what is the distribution of V? What, like, if you generated millions of values of U, and you created a distribution, it's going to look uniform, right? From 0 to 1, by definition. Okay? What will the distribution of V look like? It'll just be a mirror image of that. And overall, the distribution of V itself, in the long run, is also, well, not even the long run, it is exactly the uniform distribution from 0 to 1. So V also comes from uniform 0 to 1, okay? And that's all we're doing. It's just, when people see this, they feel like, oh, it's unnecessary to have this, okay? And so they'll just rewrite it this way. Because the goal is to get values from the from the exponential distribution. We just want random values from the exponential distribution, okay? Yes, when we derived it, we have this, but we can recognize that this is just, that thing is going to have the same distribution. Okay. Good. Any other questions? All right. Discrete case, same thing. Just it looks a little funny. Not looks, but all right, let's do a discrete distribution. All right, so our probability mass function will be defined with this table. Let's say x can take on the values 1, 2, or 3 with probabilities 0.2, 0.5, and 0.3. Okay, So if we graph the PMF, all right. So here, that's what our PMF looks like, right? Okay, what is the CDF of X? Okay, the CDF is going to be, what will this look like? So it will be it's the cumulative distribution function. So at at 0, what's the value of my CDF? 0. At 0.9, what's the value of my CDF? Okay, and at 1, what's the value of my CDF? 0.2, right? So what we have is we've got for x less than 1, our CDF is 0. And then what's the CDF of 1.5? It's still 0.2, right? Okay. And we end up getting this, and then like that. Okay. So we have it's 0.2. That's what we have, right? So this is our CDF because it represents our cumulative function. And it tells you, what is the probability that of getting a value of x or something less. Okay, so what is the inverse CDF? So the problem with the inverse CDF is that if I take this and I flip it along the axis y equals x, these horizontal lines become vertical lines, which is a big no-no in functions, right? In functions, each value in the domain can map only to one value. And so if they become a vertical line, then what value does point2 map to? It can't map to a range of values from 1 to 2. That's not allowed. Okay? So what ends up happening is that we have to use this min f inverse of u is going to be the minimum value of t that satisfies the condition f of t is greater than or equal to u. Okay, so this becomes so I've got u and f inverse of u. And basically, we have to map from the value 0 to 1 to these values, either 1, 2, or 3. Okay? Right. Okay, so what values will map to 1? Okay, it's basically everything zero less than u less than or equal to 0.2. I guess I can do that. Okay. From 0 to 0.2, it will map to 1. Okay. And then from 0.2 to 0.7, it will map to 2. And then from 0.7 to 1 will map to 3. Okay, so u is defined on the interval 0 to 1, and it will map to all the values in x. And so this graph is a little, how do we do this? So 0 to 2. 1, 2, 3, and we go from here to here. 2, 7 to that. Okay. Are there any questions here? For discrete random variable? How would we just code up something like this in R? R doesn't have switch statements, so you would just have to say, you just have to have a bunch of this might not be the best way, but like, I mean, with 3 you can write a bunch of if and if else statements. I mean, not a bunch, just you only need 3, right? If it's between 0, like generate u, and if it's between 0 and 0.2, then it's 1. If else 0, less than 0.7, then it's 2, and else 3. Okay. But what if there were 100 values of x? How can we? Oh, I'm running out of time. Okay, well you can run a, so if you have like 100, like if there's 100 cases to check, you don't want to have to write 100 else statements, right? So what you can do is you can create a loop that you basically set up a vector of the cut points, of the endpoints, a vector of 0.2, 0.7, and 1, and then you'll just basically have it run through and see, is it or you don't even have to do a loop. You just turn it into kind of a true false. Let's say the value you generated was 0.6. okay? And then you have the vector of cut points, and then you just see, is 0.6, less than the, the vector of cut points. So let's say here's your cut points. 0.2, 0.7, and 1, okay? And then you have u is equal to 0.6. And then you say, is u less than cut, okay? And then it's going to say false, true, true, right? And then so now you can use this, and you can say, well, how many of these are false or whatever? And this will give you a sense of where the value lies to figure out which value it should map to. Okay, it looks like I've run out of time, so we'll end here, and then we'll see you guys on Thursday, okay? And we'll continue on this topic of generating random values.